This year, we have studied seismic interferometry using passive seismic data, such as earthquake and ambient noise data. In this talk, we use local earthquakes for extracting reflected body waves. Before talking about this topic, let me briefly introduce our other studies. We have two more reports in the project review book. My file is too heavy. So, in this study, we use seismic interferometry to monitor wave velocities, normal mode frequencies, and attenuation of a building. The idea of this study comes from the similarity of the data observed between inside the borehole and inside the building. Last year in the project review meeting, we talked about the seismic interferometry applied to the borehole data to monitor the temporal changes. And in this report, we use a similar technique to data observed inside the building and extract several parameters. So as applied seismic interferometry, we record the wave field observed at each receiver, each floor, with the record at the first floor. In the frequency domain, deconvolution is simply division as shown on this slide. In this talk, we call the denominator receiver is a reference receiver. After computing deconvolution, we obtain the deconvolved wave field which is excited at time 0 at the first floor, which is the reference receiver, propagating upward, then reflecting up at the top of the building. By using the extracted traveling waves highlighted by red lines, we can estimate wave velocities propagating inside the building. From each earthquake, we can obtain this deconvolved wave fields, and we can estimate the velocities. Each black dot on this figure shows the estimated velocities from each earthquake. As we can see, this is a cross plot between the estimated velocities and acceleration of the observed record at the first floor. So as we can see, the estimated velocity negatively correlates with the acceleration of the observed records. So the velocity estimated from strong earthquake is slower, which indicates that we can extract nonlinear response of this building by using seismic interferometry. That's great. The detail of this study is in the project review book. Okay, let's move on and talk about seismic interferometry using local earthquake data. The local earthquake data are observed by the same receiver array as Michael used. He used global earthquakes and we use local earthquake data. In contrast to the building data, this local earthquake data is a multi-dimensional data. So in the building case, the direction of the wave propagation and the direction of the receiver array is the same. Therefore, we consider this is a one-dimensional problem. On the other hand, in this local earthquake data, receivers are distributed on the free surface, and each net wave has some certain angle with respect to the free surface. Therefore, we consider this is multi-dimensional data. The purpose of this study is to extract reflected body waves by using seismic interferometry. The earthquake data are maintained and provided by ExxonMobil and the IRIS Data Management Center. We thank Michael Bell, Philip Brocini, and Jos van der Noot for helping us to understand this data set and the one technique we use in this study. The earthquake data are observed at the lavage field in Wyoming, and these triangles show the location of the receivers. Because of the technique we use, we confine wave propagation into two dimensions. So in this study, we use 14 receivers highlighted by red triangles, and we choose earthquakes which are located on the extension of this survey line. During the period of the observation, about 200 earthquakes are recorded, and their epicenters are shown by the yellow dots here. The red triangle shows the edges of the receiver array. So receiver number 1 and receiver number 14. The depth of this local earthquake is very shallow, mostly shallower than 10 kilometers. So in this study, we use one cluster of earthquakes highlighted by blue circles, which is on the extension of the receiver array. Because the distance of the length of the survey line is about 3.5 kilometers, and the distance between epicenters and receivers is about 180 kilometers. Therefore, the incoming wave is almost plane wave, nearly plane wave. Therefore, the target of this study is to extract reflected plane body waves. Okay. So next slide is the example of this slide shows an example of observed records in the vertical and horizontal component. This horizontal component is already rotated to align into the direction of the receiver array, which means we can consider this horizontal component is a radial component. Time zero of this data is origin time of the earthquake, and direct P waves arrive at around 30 seconds, and direct S wave arrive at around 50 seconds. First, we use entire record for seismic interferometry. So first we choose one trace, which is receiver number 5, as a reference receiver, and we compute deconvolution between entire record at each receiver with a record at trace number 5. This expression is in the frequency domain. So after computing deconvolution, we average deconvolved wave fields over all earthquakes in that cluster. After applying seismic interferometry, we obtain these wave fields. Offset 0 km is the location of the reference receiver. From these interferometric waveforms, it is hard to find any useful information of reflected body waves. Therefore, we try to improve the quality of deconvolved wave fields by using 3 techniques, such as wave field decomposition, time windowing, and multi-dimensional deconvolution. By using these techniques, we try to extract clear reflected plane body waves. Let me explain one by one. We decompose 2 components of observed records into upgoing, downgoing P and S waves. By using this decomposition, we can reduce some crosstalk between P and S waves in the decomposed wave fields. I will explain later the meaning of some crosstalk. In the 2-dimensional isotropic case, observed records at the free surface contain all upgoing, downgoing P and S waves. Therefore, if we use observed records for seismic interferometry, the deconvolved wave field contains a lot of crosstalk between P and S waves. By the way, in this figure or in this talk, W indicates observed records, U is upgoing wave, and D is downgoing waves. So by using decomposition, we try to estimate these 4 terms, upgoing, downgoing, P and S waves separately. We want to compute separately by using 2 components of observed records at the free surface and stress-free boundary condition. In this figure, blue indicates input data and boundary condition at the free surface. Therefore, we already know this blue information. And red terms are our targets. So by using blue information to estimate red terms is this decomposition. Also, Wx, Wz, sigma zz, sigma xz can be written by the summation of upgoing, downgoing P and S waves. Therefore, this blue information is equivalent to 4 equations. Because we have 4 equations to estimate 4 unknowns, we can solve this system. I will show you the procedure of this decomposition by using cartoons. These are observed records and boundary conditions at the free surface. Observed records are originally in space-time domain, and we first convert this space-time domain observed record into wave number frequency domain by using Fourier transforms. Each complex value in this domain satisfies those stress-free boundary conditions. Also, WZ, WX, sigma ZZ, and sigma XZ can be written by the summation of the upgoing, downgoing P and S waves. So these are equivalent to 4 equations. And we can use these 4 equations for solving upgoing, downgoing P and S waves. These are still complex values in the wave number frequency domain. Finally, we convert these wave fields into space-time domain by using the inverse Fourier transforms. The reason why we use Fourier transforms is we don't want to estimate the angle of incidence at each wave or each point in the space-time domain. By using Fourier transforms, we decompose wave fields into different wave numbers, and we don't have to estimate the angle of incidence because of the relationship between wave numbers and the angle of incidence. This is an example of decomposed wave field using the earthquake as I used before. In this decomposed wave field, P and S waves are separated. Therefore, by using this wave field for seismic interferometry, we can reduce crosstalk between P and S waves. The second technique is time windowing. The purpose of time windowing is to separate direct and reflected waves to suppress crosstalk between direct waves at the different receivers. This is a very simple cartoon of the wave propagation from one source to 2 receivers. We draw only 2 direct waves and 1 surface-related reflected waves. In this study, we use Bray waves, so the reflected waves recorded at receiver B are always first recorded at receiver A. So the reflected waves are first recorded at receiver A, they propagate to receiver B. When we decompose the record at receiver B with the record at receiver A, this combination contributes to reconstruct the reflected waves propagating from receiver A to receiver B, but this combination is not. This combination creates crosstalk between these 2 direct waves, which we are not interested in. Therefore, by using time windowing, we separate direct and reflected waves, and we use only the combination between direct waves to receiver A and reflected waves to receiver B to improve the quality of extracted reflected body waves. After using time windowing and wave field separation, we obtain these reflected waves. These are PP, PS, and SS reflected body waves. We can also extract SP reflected waves, but we don't show here. Offset 0 km is the location of the reference receiver, and for display purpose, we use time reversal before computing deconvolution. So all reflected waves are in the negative time. To estimate the arrival time of reflected waves, we just simply compute the absolute value of these times. Because we compute deconvolution between each pair of traces, we call this is trace by trace deconvolution, or T by T deconvolution. Based on slant stack assumption, based on plane wave assumption, we slant stack the waveforms along the blue line, and the right panel shows the stacked waveforms. These waveforms are much clearer than the original decomposed wave field using entire record. However, these are still noisy. For example, because we use time windowing, the amplitude below the blue line should be very small, but these are not. This is based on causality. The reason why this there are some amplitude is that trace by trace deconvolution needs some assumptions. Trace by trace deconvolution is based on this cartoon. When GPP represents PP reflected wave propagation from receiver A to receiver B, and superscript of R represents reflected waves, reflected outgoing P waves at the receiver B can be written by this expression in the frequency domain. When we want to extract GPP, we simply decompose reflected outgoing waves with downgoing wave. Again, this is in the frequency domain expression. This expression looks good. However, we ignore several waves in this expression. For example, downgoing S waves also contributes to the reflected outgoing P waves. Therefore, after computing trace by trace deconvolution, this red term remains as crosstalk between P and S waves. This expression indicates that even if we use wave field decomposition, we cannot completely suppress crosstalk between P and S waves by using trace by trace deconvolution. Also, downgoing waves from other receivers contribute to the reflected outgoing waves. So these blue terms are the crosstalk between different receivers. This crosstalk decreases the quality of decomposed wave fields. To further improve the quality of decomposed wave fields, we employ multi-dimensional deconvolution. Using MDD, we can reduce crosstalk between P and S waves and between different receivers. In MDD, we do take into account downgoing S waves and all receivers. Instead of computing trace by trace deconvolution, we solve an inverse problem based on this matrix equation. The middle matrix is the grid matrix, and GPP, GSP, GPS, GSS are our target. Here, the curly G is the matrix of the Green's function as shown at the bottom of this slide. X and Y are either P or S waves. Using wave field decomposition and time windowing, we already obtain reflected upgoing waves and downgoing waves. Therefore, we can solve this equation for estimating the Green's matrix. After solving this inverse problem, we obtain decomposed wave fields in PP, PS, and SS reflected waves. Note that these MDD wave fields don't include any crosstalk between P and S waves, between direct waves, or between different receivers. Compared with the trace by trace decomposed wave fields, 2 points are significantly improved. The first point is coherency between traces. In MDD waveforms, we can extract clearer plane waves. The second point is the amplitude below the blue line. In MDD wave fields, the amplitude is much smaller. Based on these 2 points, we conclude that MDD improves the quality of decomposed wave fields. Compared with the original waveforms using entire levels, the difference is obvious. From this original wave field, we cannot extract any useful information on reflected body waves, but from MDD wave fields, at least we can find 3 significant reflected waves. The arrival time of these reflected waves correspond to the reflected waves from one reflector which was discovered by a previous study. This is a velocity model and geology of estimated by the previous work, and my receiver array, our receiver array is this area. The reflected waves in MDD waveforms come from the strong reflector at 3.8 kilometer depth. In summary, we use We use wave field decomposition, time windowing, and multi-dimensional decomposition to improve the quality of decomposed waveforms to extract clear reflected body waves. For future work, we'd like to use this technique for time-lapse monitoring. Thank you for your kind attention.